So yeah, thank you very much for coming along to our Statistics Across Campuses seminar for today. And I'm very happy to introduce Willem van den Boom from the National University of Singapore. He's currently in the School of Medicine, but did his PhD in statistics from Duke in 2018 and has been working in a bunch of areas, including Bayesian inference. And so today he'll talk about Bayesian learning of graph substructures. So Willem, I'll hand the floor over to you.
Thank you very much, Shahani, for the introduction, but also for the invitation to speak. So please feel free to interrupt me if you have any questions along the way. So I'm talking about Bayesian learning of graph structures. Before I get started, I would like to acknowledge my collaborators. So my postdoc supervisor, Maria Di Orio, and Alexandros Veskos from UCL. So Bayesian learning of graph structures is about the following. So we're looking at graphical models. So graphical model is a model where there's an underlying graph that captures like the dependencies among the, like, say, multivariate data. And so in these graphical models, there's been lots of effort just trying to infer these graphs. But people haven't, in this graphical model literature, there has not been as much attention on trying to find, say, large scale structure in these graphs. On the other hand, there's a whole literature on random graphs, and there people have been looking a lot at, like, these large scale structures. And these motivations from random graph theory to look at large structure, they also apply to graphs and graphical models. So we basically set out to kind of say, okay, let's try to detect these large scale structures, not just also in, like, say, the graphical models. And this has benefits. So the large scale structure can help you with interpretation. But it can actually also not just with interpretation. If there's, like, any kind of large scale structure present, if you're able to identify it, it can actually also then help the graph estimation itself. So the approach that we're taking here, like one specific, more concrete direction, is that we use a block model as a prior on the graphs. And then so that's a prior on the graphs within a bigger graphical model. So let me talk a bit more about graphical models and random graph theory. So I already mentioned graphical models are modeled for multivariate data. So there's a graph that captures the conditional independence structure. And so it's a big area of work. There's even different types of graphs, like directed graphs, indirected graphs, chain graphs, directed acyclic graph. There's lots of different types of models that fit in this. Here we'll be focusing on undirected graphical models. The next slide will give a bit more details. But in general, these methods, they focus on just recovering the graph in the sense that they focus on basically estimation of individual edges. So they don't really focus on really recovering logical structure of the underlying graph. This kind of is, like, in contrast with random graph theory, which doesn't care about multivariate data, but just looks at graphs. So they model graphs rather than, say, continuous multivariate data. And this field kind of, has a long history. Like in the 50s, the Adios ranking graphs were introduced, where they basically said, okay, each edge is, like, independently absent of presence with say, a Bernoulli distribution. So that's a very simple construction where you don't really have any kind of large scale structure, but that was just a starting point. And since then, it has, like, evolved a lot. And one of the most popular ways of kind of capturing large scale structure in graphs are these models known as stochastic block models. So here we basically kind of marry, in a way, push together more these two kind of separate literatures to kind of get something that's I think is also useful in graphical models. So Gaussian graphical models. Graphical models. Graphical models talk about conditional dependency. We specifically talk about Gaussian graphical models. It just means that the multivariate data that we're looking at has a Gaussian distribution. So we have some Gaussian distribution. So it means we just have some covariance matrix, or in this case, we're looking at the inverse, at the precision matrix. And somehow there's a graph involved. So what, in, like, an undirected graphical model, so this graph is going to inform the precision matrix. So in an undirected graphical model, the absence or the presence of edges says something about the conditional independent structure. Specifically, if an edge is absent, say between node 1 and node 3, that means that of the multivariate data that you're trying to model, say the first and the third variable, or the first and the third dimension, they're like independent of each other, given all the other dimensions. So in this case, it will be like the absence of this edge in this graph with 3 nodes means that y1 is independent of y3 once you know y2. So this is kind of like an attractive way to kind of capture conditional independence. Once you have such a graph, then this conditional independence actually translates to something in the precision matrix of if you're talking about the Gaussian distribution. So let's say we model here so basically this conditional independence here means that the corresponding element of the precision matrix is equal to 0. So this element 1, 3 is equal to 0. And we can kind of make this a bit more precise by saying, okay, the graph consists of a set of edges, and whenever an edge is absent, then the corresponding element of the precision matrix has to be 0. So the graph basically constrains the precision matrix, and then the precision matrix models the data. So this is like the likelihood, and now we're trying to infer the graph. That's now the challenge. So we do Bayesian inference here, so we need some priors to kind of get this to work. So we use some hierarchical prior to do this. In the tab, we put a prior on the graphs, and we put a prior on the precision matrix. And for the prior on the precision matrix, we don't do anything very special in the sense that we use the G-Wisher distribution, which is a fairly popular approach for this. It's basically a Wisher distribution that is truncated to the matrices, the precision matrices that satisfy the graph constraint. That seems like a simple construction, but actually in practice it's not that simple, because the truncation results in a normalization constant of the prior distribution that is intractable, and it depends on the graph. So it's intractable, and because it depends on the graph, you can't ignore the normalization constant if you're trying to infer the graph. So actually you have to do some advanced MCMC for posterior computation, but that's not the topic of today's talk. But actually we had some earlier work to actually make this work, to be able to actually practically do this with the sizes of graphs and the kind of posteriors that we're looking at. So that's prior on the precision matrix given the graph. Then basically this talk today is about the prior on the graph. So we're trying to capture logical structure. So we're going to specify specific priors on the graph space that somehow capture logical structure, like it inverts logical structure. And specifically, we'll be focusing on stochastic block models. So a stochastic block model, one way to define it is to say it's a partition of the set of nodes. So a graph consists of nodes and edges. Edges are between nodes. And then you can say, okay, well, let's say there's some kind of logical structure where there's like groups of nodes. And within the groups, there's a more connection between nodes. So there are more edges than between groups. So yeah, so these groups are then kind of communities, and then we refer to them as blocks. And then these if once you have the blocks, well, you basically have a partition of the set of nodes. So that's the stochastic block model. So to kind of infer then a stochastic block model, to kind of fit it, you have to infer a partition. Well, one way to kind of fit partitions is using Bayesian nonparametrics. So that's what the approach we take here. So we take the model from Tan and Diorio, which basically gives us then a prior on a partition. It happens to be computation convenience, and basically kind of it has some virtues from the Bayesian it has some virtues from being Bayesian nonparametric. Namely, it gives you like this data-driven clustering, and also like we have, for instance, a random number of blocks. So we don't have to pre-specify, say, the number of blocks beforehand. But this is just this random graph theory literature here that we're using here to specify this prior on the graph. So let me give some more details. So we have a prior on the graph. So we basically have a prior on the edges. And so we're going to just assume like the edges are like conditionally independent. So given the parameters, actually each edge is independent. So all we have to specify is just the probability of the edge being present. Well, we basically just use some kind of probit model. So this phi inverse is like the inverse CTF of a Gaussian distribution. So it takes its probability and it maps it to the whole real number line. And then how do we then model this transformation of the probability? Well, we have some popularity parameter theta, which kind of gives a sense of like the overall level of connections between nodes. And we have this beta term, which is specific to the to say to each community. So it kind of captures how many edges there are within a community. And so this beta is an interaction parameter. So, and here on the right, we have these z's. These z's are like allocation parameters. So zi indicates which community node I belongs to, and zj indicates which community node j belongs to. So in case they belong to the same community, then they have the additional interaction beta. So there's additional propensity to connect compared to when they were not in the same community. So here on the right in the figure, it's kind of like marked a little bit. So we have, say, 3 communities, say z equal to 1, z equal to 2, z equal to 3. And as you can kind of already see, like there's more edges within the community. And then the green edges kind of like correspond to this beta parameter, like, okay, they are like more likely because of this beta parameter, this interaction parameter. And then there's also still a baseline probability given by theta of just any edges connecting, including edges between groups. So that's here given by theta. So we're interested in the block structure. So we're interested in firming Z's. So we actually don't have put directly a model on Z. What we actually do, we have some fancy way of, we actually do something on the betas that kind of gives us jointly a model on what the values of betas are as well as what the Z's are. So we use a Dirichlet process. So we have betas distributed according to H, where H is a Dirichlet process. So that means that H is a discrete distribution. And so this discrete distribution is going to make, it's basically going to cluster these betas. So we have P different betas, where P is the number of nodes. But then due to the Dirichlet process, we have fewer than P unique values. So we're basically clustering the betas. And then whenever 2 nodes have the same beta, then we say that they belong to the same block. So then we say they have the same allocation, the allocation variables to be equal. So we just basically use the Dirichlet process both for clustering as well as to infer like what the value is for this interaction parameter. So this is a Bayesian non-parametric stochastic block model. Effectively, for one way you can look at it is it specifies a prior on the partition. So Z parameterizes the partition. Then given the partition, it's going to give us a distribution on graphs. So that's this probit expression basically up there. So now we have a prior on the graph space. Well, given the graph, we have a prior on precision matrices. That's a G-Wisher distribution. And then given the precision distribution, given the precision, we have a Gaussian likelihood. We know the likelihood. So this now specifies a posterior distribution. So we have this posterior distribution, basically a standard Gaussian graphical model tied with this stochastic block model. And now we can see what happens. So we're going to apply it to some data. So the data consists, so the data here we're looking at is like financial data. It's returns of mutual funds. So here we're looking at 59 mutual funds. So basically our graph now has 59 nodes. And we have 86 observations. So that's just the number of observations we have of this multivariate Gaussian distribution. So that's the data. Why do we like this data? Well, it has, for each node, for each fund, we know which sectors they invest in. So that kind of gives us like a reference structure. Like if they invest in the same sector, you would expect that they are somehow more similar. So you would maybe expect more edges between them and maybe them supposed to be blocked together. So this kind of gives us like some kind of baseline that we can compare with what our method ends up inferring. So we're talking about, hey, what it infers in terms of blocks. Well, that is this kind of posterior that we're interested in. We're interested in the posterior on the partition. And there's a different way to look at this. We'll be looking at the posterior similarity. So just checking, okay, what's the posterior probability that 2 nodes belong to the same block? We can also look at a point estimate. So specifically, we'll be looking at the point estimate of the partition that minimizes the posterior expectation of Binder's loss. So that's a certain loss function that is commonly used within the Bayesian non-parametric literature. It's just to give us a point estimate, something, another thing we can assess. So this is all about the partition. You can still wonder about, hey, but what about the graph? Because that's what we started with. Well, we also look at something known as the median probability graph. So graph space is super big, and you get a posterior on this huge space. So one way to get a point estimate is to say, okay, I'm going to draw the graph, and I'm going to include all those edges which have a posterior inclusion probability that's greater than 1/2. It's known as the median probability graph. So those results are shown here in this slide. So here on the left, we have these posterior similarities. So on the X and the Y axis, we have the funds, and then the plot basically shows the posterior probability that any of these 2 funds are like blocked together, are in the same block. So what do we see? Well, we see kind of these, and by the way, the red dotted line kind of demarcate these known groups like the sector C investing. So the first, for instance, the first block invests in US bonds. So the first block invests in US bonds, and we see that our model kind of nicely all groups them together. So you see they have like a stereo similarity equal to 1. So for the other groups, that's not entirely the case. So for instance, something that's kind of a bit interesting is if we look here at the US stocks and bonds, so this is kind of like the third block here, the US stocks and bonds, they're like blocked together with the US stocks. This, I mean, arguably this makes sense because, I mean, US stocks and bonds include US stocks, so it might make sense that they're like being grouped together. So also here on the right, we have like this, basically have with colors, we have this reference blocking structure, and then the black boxes, they indicate the point estimate of the partition that we obtain from our posterior. And we see here the same thing. So we have in blue, we have all the US stocks, and we see that together with the US stocks, we have in red, we have the US stocks and bonds that are grouped with them. And then we have, say, another block with mostly international stocks. And the first block, the US bonds thing, it's entirely on its own. And I mean, US bonds behave quite differently from stocks. So that's in a sense also not unreasonable. So this is this graphical model with the stochastic block model, and you find some partition. Now, just in a general thing about when you have a posterior on a partition, you might wonder, well, hey, was it worth it to do the partitioning? Like, is there evidence for any blocks? Well, in this case, you might say, yeah, clearly there's evidence for blocks because the posterior probabilities are like close to 1/0. Yes, that's true. But in other cases, it might not be as obvious whether it makes sense to take all this effort to take some clustering approach rather than just throw, say, all nodes in this case together. So for that, we considered some kind of testing. So basically try to test whether there's block structure, yes or no. So what you can basically say is, okay, do we have, say one hypothesis, say, okay, yeah, the partition is actually distributed according to a prior. So it means that there's some block structure versus say, no, there's no block structure, say that everybody's in say same block. So that's basically our hypothesis testing problem. And one way to approach this in a Bayesian framework is to do compute a Bayes factor. So in these complicated models, computing the Bayes factor is often not straightforward. So for these partition models with, say, these Dirichlet processes or other Bayesian non-parametrics, something that people have done is use the harmonic mean approach. So it's very simple. You just compute the harmonic mean of the marginal likelihood of your MCMC samples. So it's very simple, but the downside is that it can be quite unstable, and it can also be hard to assess, say, whether it's unstable. Because basically, I mean, you have a consistent estimator of the marginal likelihood, but it's not guaranteed to have finite variance, so it can be problematic. Then there's also other methodology that kind of tries to get around it, but it's also specifically for these partition models, but it's quite a bit more involved in the sense that you can't just compute it directly from the MCMC run. You actually have to create a separate MCMC chain and that you run with, say, something related to C star, you like to pick C star in some way, and then you have to do some computations. So here we looked at using the Savage-Dickey ratio to compute this Bayes factor. So this ratio of marginal likelihoods. So the Bayes factor is this ratio of marginal likelihoods where it's like either the marginal likelihood given C star, so say there's no blocks, and divided, say, by the marginal likelihood of our model. So that's where the partition is distributed according to a prior. So we can just write it like that, like the marginal likelihood given C star, or the likelihood given C star divided by the marginal likelihood. So these quantities are hard to, especially these are hard to compute. But we can, using Bayes rule, we can rewrite them. So we can write them basically as the joint probability divided as the product of the probabilities of Y and Z star. And then, and because of the way we set up our model, we can do this because basically the two models are like the two models have a comparison with hypothesis and a way compatible. So aside from Z, they basically use all the same priors. And then, so at the end, we end up with this expression. So again, by Bayes rule, we have that. I mean, if we just look at this term here on the this term here, it just reduces to this conditional probability. It's just a posterior probability of Z star, say having no blocks. So why is this nice? Well, the top term we can kind of straightforwardly estimate from our MCMC. So we can just see what proportion of the time does our MCMC chain visit Z star, in this case then say no blocks, like or everything together in one block. And that gives us an estimate of that probability. The term at the bottom, we can often compute analytically, or even when we can't compute analytically, we might be able to do a simple numeric quadrature if there's say some hyperprior involved, or we can do some just some simulation from the prior sometimes to get a sense of what that probability is. Okay, by the way, this almost seems too good to be true, in the sense like, well, have people done all this work and now it seems to be such a simple solution. I must admit here, this is only going to work when this denominator is large enough. Because if the denominator is super small, then regardless kind of what your base factor is, unless your base factor is super large, you wouldn't expect your MCMC chain to visit Z star often, so you can't get a good estimate of the numerator. But in the case Z star, the probability of Z star in your prior is kind of relatively large, then things should be fine, even if your posterior chain doesn't really visit Z star often. Okay, if it fails to visit Z star, because if then it fails to visit Z star, and you know that it's Z star, and you know that it has a high probability on the prior, you know that's basically just because there's like this probability is actually small. So then it's accurately estimating, say, the base factor to be 0. So this is just kind of a computational trick I want to share with you about base factors that we actually use in this work. So we talked about stochastic block model. So the next thing I want to do is just talk about an extension. So originally when stochastic block model came around, actually before, when people were talking about communities and saying networks and social networks, the earliest ideas in these block models were not so stochastic. They more had, they had a situation where basically each community has, say, all edges present. So rather than say have some stochasticity within the communities, they basically said, okay, if you're in the same community, you're always connected. And it's more like a simpler structure. And like from, say, a sociology perspective, that can make a lot of sense. So in the random graph theory, people don't really focus on that scenario because it's not really that interesting, because as soon as you have, say, a missing edge, it breaks up your communities. But in the graphical model context, it's a different story. Like, we don't observe the graph directly anyway, so then it might make sense to have, say, a more restrictive prior on construction on, say, your structure on say, your blocks. And it could even be like motivated by the application. So for instance, protein-protein interaction networks, these blocks that have all edges present, known as cliques, have for instance, specific meaning. There's one downside here. Once we do this thing in our modeling framework, MCMC becomes harder. Why is that? Because if you now move one node from one block to the other, you have to change multiple edges because the block that node is joining now gets like all new edges with that one node that's going to join. And basically, this MCMC for Gaussian graphical models mostly involves changing a single edge at a time. So that's a bit of a challenge. So things are a bit less scalable, but we can still do this in our framework. So going back to the mutual funds example, we basically can look at the posterior similarity matrix, what it looks like with this different priors. Here on the left, we have the same result we looked at previously. On the right, we get what we have with this so-called Southern Italian community structure, with this model where blocks are cliques. I mean, it's immediately clear that, hey, the posterior similarity values are a lot lower. This is kind of, it's not surprising in the sense that once you make the definition of a community more restrictive, it's going to be less likely that blocks are going to get grouped together. But overall, you still see a little bit of a similar pattern going on. So you still see like within these red squares, you still see some higher values than, say, in like the off-diagonal, like the non-square rectangles. So stochastic block model, Southern Italian community structure. So 2 priors. Now I'm going to move to the last prior that I'll be talking about. So far we focused on a single graph. So basically all observations are like from the same Gaussian distribution. They're like IID, and we're just trying to figure out this basically logical structure related to the specification matrix. In practice, your observations are often not, say, IID. There's like, say, there's some more structure to it. Could be that, say, some observations are under treatment, the others are under control, or there could be some other type of of grouping basically of your data. So we can, so this is something that people have considered before in graphical models, and then they do something known as like, we call it the multiple graph scenario. They do like a multiple graphical model. So they basically create multiple graphs and then somehow they link the graphs together. Here we're going to try and link the block structure of the multiple graphs together. So we extend the stochastic block model in some way to multiple graphs. And this has also been done just in the random graph literature a bit, but not in a way that was, in terms of Bayesian non-parametrics at least, not in a way that was entirely satisfactory to us. Because some would either assume that, say, the block structure stays the same between graphs, or it's entirely different, but no like kind of intricate dependencies. And we were interested in a bit of intricate dependencies. So we started considering dependent Dirichlet processes. But those didn't work perfectly either. But the issue is that basically dependent Dirichlet processes, they have like a property, often typically having a property known as partial exchangeability. So that means that within one group, observations are exchangeable. Like kind of, but it's like joined at the same time across all groups. What that means is that, say, the first observation in group 1 is like not unrelated, totally unrelated to the first observation in group 2, because basically you can always exchange any of them, and the model which basically is like invariant to that. But that doesn't really jive with our context, in the sense that, say here we have these cluster allocations for, say, 3 nodes, and say in group 1 they are in 3 different blocks, and in group 2 the first 2 nodes are blocked together. If you have such a construction, you would expect that, say, if node 1 is in the blue group, you would expect it to stay in the blue group. You wouldn't say all of a sudden expect it to become a red group. You want to kind of acknowledge the fact that the first node in group 1 is also the first node in group 2. And because nodes here correspond with variables, so even though it's different groups, you're still measuring the same variables. So you want to have some kind of structure. So this is kind of a different notion of exchangeability. Well, I mean, you still have some exchangeability in the sense we want things to be invariant to nodes, to the node ordering overall, but we don't want to have exchangeability then separately within each group. So therefore, we kind of devise some kind of slightly different dependent Dirichlet process. So just to recall what we were actually using, so we have this Dirichlet process, like discrete distribution H, and the discreteness induces the partition. So that's one specific H. So how we're going to extend this to multiple graphs such that we kind of have this connection that I was just talking about? Well, we're going to say is, okay, we're going to take one group as a baseline, and then the other groups, they're going to like deviate from the baseline. So beta 1i is like, beta 1 is, say, the vector for the baseline, and then beta x is, say, the interaction parameter vector for the other groups. And then we're going to basically say you're going to each element of beta x is going to be equal to the corresponding element of beta 1 with a certain probability. So you kind of explicitly link them, say node 1 in group 1 with node 1 and node 2, etc. So you're going to do that explicitly with a certain probability. And if that happens, then they're linked, they're the same, that's fine. If that doesn't happen, say, because also, I mean, it's not the probability 1 that you set them equal, then you would assume that construct will be the same. Then you're going to say, okay, then we draw this beta xi from the same H that we were already using. So then it can still kind of join, say, an existing community or something, but it's not linked directly in the way it otherwise would. So this kind of gives you like kind of, I mean, it seems a very simple construction, but it gives us like a rich enough dependencies across graphs. And there's actually basically it defines a prior on partitions, and a similar prior has actually been recently considered for like time-varying partitions. So multiple graphs, different prior than the 2 we saw before. So now we're going to look at a different data set to apply to. We're going to look at gene expression levels. So we now have, we're going to look at some 44 different gene expressions, and they're measured in like 590 breast cancer tissues and 560 ovarian cancer tissues. So we have basically observations of the same variables, but across 2 different groups. And now we can apply our methodology. So here on the left, we have the stochastic, basically the result of stochastic block model for the breast cancer. On the right, we have the result for the stochastic block model for the ovarian cancer. And we already see that there are differences, and then you can here in the middle basically explicitly look at these differences. Say, okay, what is the probability that node 1 in the one group is in the same group as node 2 in the other group. That's basically what's shown here in the middle. So we see some differences here. So specifically, the main difference I would say I want to highlight now, just to show that we can capture like these varying community structures. So firstly, you see that there's a lot of shared structure that is picked up. But then if you look at, say, here nodes 41, 42, 43, and 44, the last three. So these are like three closely related genes. They're like blue blocked, say, with the second previously identified block. So again, the red lines identify previously identified blocks of genes. For in breast cancer, well, if you look here at ovarian cancer, these three genes are grouped with the first block. So we see that there's like some variation going on. So this is the basically multiple graph extension. Is one way to do it, say, multiple graphs in this context with Gaussian graphical models where I'm trying to learn these graph substructures. So that actually brings me to my conclusion slide. So just to repeat, like, yes, we're trying to find large-scale graph structures in graphical models. We do so with a stochastic block model, and we kind of look like at a different block model called Southern setting community structure. So we just use these as priors, and we see that we get like, if you do this, we get like nice blocks, and we can kind of try to interpret them, and like we believe like this, the general ideas are like widely applicable when it comes to people using graphical models. We looked at an extension to multiple graphs, so we have some kind of slightly different dependent Dirichlet process that allows you to kind of have some dependence between the multiple graphs, and allows for the same blocks, but also allows for different blocks, like in a kind of principled manner. So one thing I did not talk about today is this G-Wishart weighted proposal algorithm. So I alluded to it before. So this G-Wishart prior is not that easy to work with when it comes to posterior inference. So we had some earlier work to actually make it work fast enough that we could show you these results in a reasonable amount of time. But I just want to mention here that there's something called the exchange algorithm that helps us use the intractable normalization constant in the G-Wishart prior. So that's something that people have done before. That's for those of you interested in MCMC. And there's actually some more recent developments, something known as locally informed proposal, and the late acceptance Metropolis Hastings that really kind of make all the MCMC kind of shine in this whole model. But then this is Van den Boom et al. This basically this recent paper that gives details about that. So that is all being used in this work, but it's just quite a different topic to talk about. And I mentioned this Page, Quintana, and Dahl dependent partition thing that relates to the dependent Dirichlet process that we kind of presenting. So definitely, if you're interested in these kind of constructions, I think they have much more focus on that, on kind of these thinking about, okay, how can you make partitions dependent in a way that in certain contexts makes more sense than what people have been doing. And here's some more references about what I talked today. But if you want to know just the details about what I talked about, then we have like a preprint of an archive that has many more details and more references and so on. So thank you very much for your attention.
Thanks very much, Willem. It was a really interesting talk. Are there any questions?
Maybe I can start. Thanks for the talk. Just first to check that I understood, I appreciated what you did. So you are actually not given a graph, you're given nodes and you're given time series on each node. And you don't want to detect communities from a given graph, like if you use like modularity or other kind of, community finding algorithms, you want to infer, like without actually having access to the actual graph, you want to group nodes into communities. Is that correct? My understanding of?
Yes, that is correct.
Okay.
Yes, that's very correct. So we don't observe the graph. We just have multivariate data. And we want to basically what people usually do when they observe a graph, block the nodes together, right? But basically, I mean, it's not like we then take a huge step by doing something fancy to go from the multivariate data to the node blocking. No, as an intermediate step, we are estimating the graph, but we do like jointly in a Bayesian framework. So that means that all kind of say uncertainty in the graph estimation kind of is like properly propagated through the whole model. And it's really like a joint estimation approach. But yes, what you just said is right. I just want to make just one thing about you mentioned time series. Well, we basically have multiple, say, IID observations from our Gaussian distributions. So I did say 86 observations here. The 86 observations are indeed the time series, but in this case, we're entirely ignoring any time dependence.
Sure.
So, but that's just an example that people have used previously with graphical models. So that's why we use this.
Yeah. So what was the time series, or what were the observations of the Southern Italian community structure? Like, what were the data like, or were you just given the graph?
No, we're not given graphs. Okay, so we have this mutual fund data. So these are just financial returns. We applied that data to both the stochastic block model as well as the Southern Italian community structure. So the Southern Italian community structure is just the name that we gave, I'm sorry for being unclear, to this structure where communities form cliques. And that is because, I mean, Maria, she's from Southern Italy. And so she thought it was a very good idea to kind of name it after this region, given the way villages are like very closely linked within each village in Southern Italy, but then the connections between villages are much sparser. Well, within a village, you can basically assume that everybody knows each other. So there's a clique.
Okay. Then it sounds quite, do you know the work by Tiago Peixoto?
Yes. So
very
after I fully agree. So after we put up our preprint, we were not aware of his work. But he was so kind to reach out to us and make us aware of his work. And yeah, so now there's already the second version up on archive sites discusses his work. So basically he does something very similar. I mean, of course there are differences, but he has this one paper where he basically does the same thing, but we focus on Gaussian graphical models, and he focuses on different graphical models that have, I mean, effectively they're also graphical models, but his kind of like perspective is a little bit different. And then he also uses a Bayesian non-parametric stochastic block model. But it's kind of like, so we have this very probabilistic, almost like it feels more statistical to me, like to have this generated process or the edges are independent, to get some prior. He has something, I've forgotten the name. I think it was, it's called configuration model. It's a bit of a different model where you don't say model, like say the edge ID, but it's more like you model separately how many edges there are. And once you've conditioned them how many edges there are, then you assign them in a combinatorial way to node pairs or something like that. So it's a bit of he uses some different models and stuff. But yes, his work is very related. And if you go to archive paper, you'll see his work mentioned and discussed. Yes.
Okay. Thanks.
But thank you for reminding me, because it was only because he reached out to us that we were made aware of that. Because he's like, I mean, like we work in statistics, and for some reason totally missed that physics literature. Yeah, there's lots of machine learning literature also related to this. Yeah, for some reason this was like separate. Yeah, but I think it also has to do with this first part, the separation between random graph theory and graphical models. So in some way, random graph theory seems to be very big in the physics community. Graphical model seems to be slightly less so big in the physics community. Or maybe we just think about graphical models differently in the stats community. I'm not sure.
Mm-hmm.
Are there any other questions? So maybe I can ask one, Willem, about the time varying partitions that you mentioned towards the end of the presentation. I was curious if there's been any work done on Bayesian learning of time varying partitions, and if, I guess in your approach you're using MCMC to compute your posteriors, how amenable would this be if you then needed to compute a time series of posteriors?
So this Page, Quintana and Dahl paper does precisely this time varying partitioning. So basically, so we have a baseline partition effectively, and then deviations from that baseline partition. That's what we do. What you could do is just say, okay, take the baseline, take that as time 0. Then you have a deviation from the baseline as time 1. Then another deviation from that time 1 is time 2. So then you get a time series, a Markov chain of partitions. That is what here, this article here does. And they also use MCMC for inference.
Right.
So,
okay.
So just okay, so that's, and you might say, okay, but we have a whole time series, how's it going to scale and everything?
Right.
I must admit here that in our work, the main challenge was working with the Gaussian graphical model. So basically the whole partitioning part and the Dirichlet process part of our MCMC is computationally kind of negligible compared to the effort we're making to update the graph. So even once you have, say, once basically it's some kind of Gibbs sampler, like you've given the graph, you update the partition. Once you have updated the partition, you condition on the partition, you update the graph. This updating the graph is a lot more expensive than updating the partition. So yes. So also given that really a time series of, say, graphs might be, at least with the way we took it, with the computational tools that we chose to use, is quite expensive.
Yeah. Okay. Yeah, that makes sense.
Can I ask another question?
Yeah, please go ahead.
Maybe I didn't quite understand this correctly, but part of your prior is the number of communities in the block model. Is that correct?
That is correct. Though, so we use the Dirichlet process. What that effectively means is H is an infinite, it's like a discrete distribution with infinitely many atoms. So basically you're drawing this beta from a distribution with infinitely many atoms. So if you consider each atom as corresponding with one community, you're basically a priori assuming an infinite number of communities. But of course you can't have infinite number of communities if you have only a finite number of nodes. So automatically then when you say sample these for a specific graph, they're going to basically coalesce, you're going to select certain atoms, and then if two nodes select the same atom, they have like they are the same community.
Oh, so you start with each node being its own community. Is that how you start, or do you have some random partition definition?
Yeah, we have basically a random partition prior. Okay, so there's two things here. There's the model and there's the inference. So the model is just, okay, we have this setup with this H being basically an infinite number of components, and then the betas occupy a certain finite number of these components, and then the number of occupied components are called clusters, and the number of clusters corresponds with the number of blocks. But that's the model. So, and that gives you then some random partition prior. In inference, yeah, we initialize the model in some way. So I would have to check whether I initialize it with all nodes in the same community or all in separate communities. But then the MCMC does its thing. And if things are okay, like the MCMC properly converges, our results should not depend on how we initialize the MCMC.
So the reason why I'm asking is, like, let's say, I mean, you mentioned protein-protein interaction networks, but you have the same thing in social networks. Like you could look for cliques, like for protein complexes, so very tightly, very tight communities of small size. But there are also these kind of larger communities, where some functional communities or something in protein-protein interaction networks, or I don't know, let's take a suburb or something, right? You got you got your house and everyone knows each other there or something. And there's sort of, depending on the scale you're looking at, you find different communities. Is there something in your prior that you can use that to sort of kind of scan through, different sizes of communities? And like, if let's say you take a PPI network and you want to look for, complexes consisting of whatever, 20, size 20 proteins, and then, or you want to look at sort of large kind of pathways. Is there something you can do in those models to do that?
Yes. I mean, we did not. We just used the Dirichlet process, which gives you a certain partition prior, which actually has certain downsides. People have complained because with the Dirichlet process, we talk about what you just said, like the blocks and so on. The Dirichlet process kind of a priori says, okay, there's one big cluster, then there's another smaller cluster, then that's another one that's even smaller. and actually that whole process actually also causes something that people sometimes call like, okay, like, hey, the Dirichlet process gives you lots of singletons. So if you look here at the point estimate that comes out of our posterior, you see that we have like these two mutual funds that are like on their own, that are not grouped with anything. And you might say, well, I don't find it desirable. I don't want these big blocks and the singletons and so on. I want something more structured. Say indeed protein interaction networks, and you say, oh, I have a certain, say, upper bound on the community, so on. Yes, you can do that by using different partition priors. So basically, if you look at our approach, the only thing we kind of use in our inference in the MCMC, I mean, conceptually, you could write down any partition prior, but if you look at the only thing we use in our MCMC is something known as like a Gibbs type prior. So that means that you have some kind of expression or some kind of expression for the, say, the cluster allocation, the block allocation for one node, given that you know the cluster allocation for all the other nodes. And this Gibbs type partition priors is something that has been studied in the context of Bayesian non-parametrics. It includes many different partition priors. So you might have heard of the Pittman-Yor process that has like more flexible than Dirichlet process, allows you to do some things like that. If you talk about what you're just talking about, say you want to have communities of a specific size, there's some recent work on what's known as the microclustering prior, and it's also Gibbs type prior, but it allows you to explicitly set prior probabilities on cluster sizes. So you can say, okay, I'm with probability 1, I'm going to say a priori that my clusters are between size 3 and 10. You can specify something like that. Or I'm going to put a geometric distribution on the cluster size. With the microclustering prior, you can make explicit assumptions like that. Yes.
Thank you. But you could also run, can you run it kind of first just to actually construct the graph and then do something else like, random walk of different lengths and stuff, and then kind of do some spectral analysis of the graph Laplacian or something? Is that possible? Like first use your Bayesian inference to actually construct the graph and then use kind of standard, tools from complex network theory or so to do that. Is that a good idea, or can you comment on that?
Yeah, so people have done that. So here the red dotted lines actually come from an approach like that. So it's where they first took the gene expressions, estimated the graph, then did some spectral analysis to find these blocks. But you don't have to do spectral analysis. You could do anything at that point to find the blocks. Yeah, from a Bayesian perspective, it's like, okay, you're definitely losing, in a way, information or somehow underestimating uncertainty or something if you take this approach. So, for instance, one of the benefits I mentioned is like, hey, the large scale structure can guide graph in graph estimation. And so if you take this two-step approach, you lose that, for instance. But yes, the reason why I would do such an approach is because it's probably computationally a lot more scalable. Because this joint approach and with this Gaussian graphical model that we're using, things are not always as scalable. And if you take a two-step approach like that, you can maybe scale it up to much larger networks or not much bigger data sets with many more dimensions. Yes. Yeah, thank you very much for those questions. So it's actually coincidentally many of, especially the last two questions that you asked, they both have a paragraph dedicated to them in the preprint, because these are like things people might ask. Yes, these are.
Sorry,
I say both questions that the last two questions that you just asked, these are like very sensible questions. So both of them have like a paragraph dedicated to them in the preprint. Yes, because it's good. Yeah, these are good questions. Yeah, these are the right questions to ask about these things.
Okay.
Yeah, then I just finished teaching I'm teaching a course on PPI networks as biologists and interdisciplinary units. So that's why these questions kind of, I'm in that realm of thinking at the moment. I just finished it like an hour ago.
I see. Yes, I don't know too much about protein interaction networks. It's just that we
Me
found this
neither.
reference that was very clear about these cliques being very important in that setting. I thought, oh, that's good, because we had this idea, and in some cases it makes sense, but now we had a very explicit reference saying this is relevant for protein interaction networks.
Yeah.
All right, then. So if there are no further questions, I might close the session for today and thank Willem once again for a very nice talk and for the very interesting discussion afterwards as well. So have a good evening, everyone.
Thank
Have a good
you.
weekend.